Hey guys, and welcome to the first video in my new series of videos that I'm going to be doing on electromagnetism. This is going to be a brand new topic for this channel, and we're going to be going through the basics of electromagnetism. And this is going to be sort of aimed at university physics level, so this is undergraduate physics level. And this is going to be the first in a series of online lectures that I'm going to do as part of a movement to online lectures due to COVID-19. So that's what I'm going to do. So the first couple of these videos are going to be going through the maths needed for electromagnetism. There's not going to be too much on the maths, but there's a little bit of maths that should hopefully be familiar to you if you're doing like a maths class alongside electromagnetism. This is the sort of stuff that they'll most likely cover. So I'm just going to be kind of summarizing the maths in the first couple of videos, and then after which we'll get right into the physics. So let's get stuck in. So I'm going to start by talking about vectors. And vectors are pretty important when it comes to electromagnetism. So what is a vector exactly? Well, you've probably heard of a vector by now. It's a quantity, so say this quantity A, and it has both a magnitude and a direction. So we represent that, or the way I'm going to represent that, is by drawing a little arrow over the top, just to show that it's a vector quantity. A scalar quantity I'll just represent like normal, just with A, but a vector quantity I'll represent like that, and that shows that it has both a magnitude and a direction. And visually, you can kind of think of it as being like an arrow. So the length of the arrow obviously being the magnitude, and the direction of the arrow obviously being in the direction. So that's kind of how you can think of a vector. And lots of quantities like the electric field strength and the magnetic field strength and the force, a lot of these very electromagnetic quantities will be much better represented as vectors, as we'll see. So that's basically what a vector is. I assume you guys know how to add and subtract vectors, so that's basically that. I'm going to cover what the dot product is between two vectors. So this is vector multiplication. You guys have probably done this before. There's a really annoying fly in my room. So the dot product is basically measuring the projection of one vector onto another. So what do I mean by that? Well, say I've got one vector here, let's call it vector A, and I've got another vector, vector B. And the question I want to ask is, what is the net effect of these two vectors if you have two vectors acting on the same sort of thing? So say these are forces. If these are two forces that are acting on the same thing, how big is going to be the common direction, if that makes sense? And the way you do that is you actually put these vectors tip to tail right here, and you look at the projection of one of them onto another. As you can see, these vectors are pretty well aligned. So the way in which you quantify that is you actually take the cosine of the angle in between them, the cosine of theta. And obviously, if theta's 0, then they're perfectly aligned. They're just going to be two vectors right on top of another. But if they're like 90 degrees apart, if theta's 90, then you can see that these two vectors are going to have nothing in common, and they're going to act in completely different directions. And we actually call that orthogonality of vectors. So these two vectors that I've drawn right here, these are orthogonal. So the way in which we quantify the dot product between two vectors, so we say A dot B is equal to the magnitude of A, which is of course a scalar. Sometimes we just put like square brackets either side just to represent magnitude, times the magnitude of B times the cosine of the angle in between these two vectors. Now you notice the dot product returns a scalar quantity. So this quantity right here, a dot b, is a scalar, which is quite important. So it takes two vectors and returns a scalar. And the way in which you work out what the dot product is, if you're given each component, is you multiply the component of a1 by b1, and you add that to a2 b2 plus a3 b3 plus however many you've got. And that's if you've got a vector which has components a1, a2, a3, and b1, b2, b3. So that's how you compute the dot product. So you just do a1 times b1 plus a2 times b2 plus a3 times b3, and of course that will return you a scalar. So that's the dot product. What about the other one, the cross product? Again, you guys have probably heard of the cross product before. Quite useful, certainly in electromagnetism, to know what that is. The cross product intuitively basically gives you the vector that's normal to the two vectors you're trying to multiply. So let's say we've got our vectors a and b again. The cross product will return you a vector that's kind of normal to both. So if you imagine there's some kind of plane here where a and b are in like the same plane, then this vector here, which is a crossed with b, is going to be normal to this plane right here. So it'll return you a vector in that direction, but what's the magnitude of that vector? Well, if you imagine you've got two vectors a and b in the plane, here are two vectors, then they're going to kind of form like a parallelogram, if you see right here. So if they're not like perfectly at right angles here, then this shape right here, this is going to be a parallelogram. As you can see, if this angle here was 90 degrees, then it would be like a perfect rectangle. But it actually, in the general case, will give you a parallelogram. So what's the area of the parallelogram? Well, the area of a parallelogram is this side times this side multiplied by the sine of this angle right here. So that's going to be a b times sine theta. That's the area of this parallelogram right here. And the area of this is actually the magnitude of the cross product between these two vectors. So this vector right here has a magnitude of this ab sine theta. So we can write the cross product as vector a crossed with vector b is equal to the magnitude of a, or the length of a, times the magnitude of b times the sine of this angle right here. But there is a key difference in the cross product, and of course the cross product is returning a vector right here, and for that we need to add some kind of unit vector. You guys probably know about unit vectors. It's some kind of unit vector that's pointing normally from this plane that a and b is in. So we're just going to add a little n hat, and that just literally says point in the direction normal to both of the vectors right there. So that right there is the cross product. That's kind of the visual interpretation. Now, to compute the cross product, if you're given two vectors with their components, you guys probably know you've got to do the determinant. So I'm not going to write all that out, but basically, yeah, you do the determinant method with each component, and yeah, so that's the cross product, and here's the dot product as well. So we're going to be using them a lot in electromagnetism. So now I want to talk about the differentiation of a vector. You guys are probably familiar with the concept of differentiation, but with vectors, it's very important to know some of the specific notation and ways in which you differentiate a vector. So we're going to kind of try and combine our knowledge of differentiation along with vectors. So of course we're in a 3D space. I'll go on to talk about different coordinate systems very soon actually, but I'm going to just talk about vector calculus because of course it's a very important topic. But yeah, obviously most electromagnetism problems are going to be in 3D space. So vectors are typically going to have 3 components. And so say we have some typical vector right here. Well, we're going to have a vector which could, in theory, depend on all of the coordinates. So here's our vector A. It's going to have 3 components, AX, AY, and AZ. And in theory, each of these could depend on both X, Y, and Z. So you're going to end up with 9 different partial derivatives. And it's useful to define this right here. And what is this funny upside down triangle? Well, this right here is called the del operator. And what it does a few different things actually, depending on how it's used. And I'm going to go through the 3 different ways in which this del operator is used. And as you'll see, it's quite closely linked to what I was talking about earlier when I was talking about dots and cross products. So let's get right to it. So the first thing I'm going to introduce, which is quite an important topic, is a field. Now fields are very important when it comes to electromagnetism. And what a field is basically a thing which has a value at all points in space. And so the simplest example is something like a temperature field. So say you have a room and like the temperature has a certain value at each point in the room. So you've got some big room right here, and say it's like quite warm in this part of the room, maybe a little bit less warm in this part of the room or something like that. The temperature field is going to have a value at all points in space. So over here it might be something like 15 degrees, over here it might be something like 7 degrees or something. So it's a spatially dependent field, which is what I'm talking about, the temperature field. So what we say is the temperature, which of course is a scalar quantity, is a function of r, which is the position coordinate. And we're going to be calling r from now on the position vector. Now, of course, in a room, you're going to expect heat to flow from this part of the room to this part of the room. And so how do we kind of quantify that? Well, we know we can actually quantify it with this del operator right here. And of course, you know from like maths that differentiation will actually give you the gradient of a slope. And so the first way in which we use this del operator is by finding the gradient of a 3D vector field. So when we take the gradient of this temperature field right here, we're actually finding how much heat is flowing from the hot regions of the room to the cold regions of the room. And so obviously if you have a sharp temperature gradient, so say this right here, it's 15 degrees in this part of the room, 7 degrees in this part of the room, there's obviously going to be a really, really sharp heat flow from here to here. Whereas if, say, you have this part of the room and then you have a slightly cooler part of the room right here, so say this bit's like 16 degrees, this bit's 14 degrees, then you're going to have much less of a temperature gradient at this part of the room than you are at this part of the room. And so this quantity right here, grad T, is going to be much, much less for this part of the room. And so this is what the gradient operator does. It basically acts on a scalar field to produce a vector quantity which measures how much the quantity is changing. So there's a big change at this part of the room and a small change in this part of the room. So that's basically what the gradient operator does. And it's probably useful to write it out in component form. So say you're in a Cartesian coordinate system, so r is simply x, y, and z, the three spatial coordinates. Then grad t is going to be dt by dx in the x hat direction plus dt by dy in the y hat direction plus dt by dz in the z hat direction. So you notice that this produces a vector right here. So this, because obviously there's three different components, it takes in a scalar and it outputs a vector quantity. So this is what the gradient operator does. That's how you compute it, and what it's actually measuring is how much of a change in this quantity t is there at a certain point in the room. So you could do the differentiation and then you can evaluate it at, say, this point here. So you plug in what your x, y, and z is, and then you can literally find out how much the temperature is changing at that point of the room. So that is what grad t is, and that's what the gradient operator is. So from this you can kind of see what this funny del thing actually is. So we've got basically a vector quantity right here, and it's coming from this right here, this scalar quantity t. So this del is actually a vector quantity, but normally we don't actually bother writing the little arrow over the top for some reason, even though that would make a lot of sense. So what it actually is basically a kind of package of different derivatives in the various different spatial coordinates. I'm going to keep it simple and keep it in Cartesian for now. But what this del is the derivative with respect to x in the x hat direction, plus the derivative with respect to y in the y hat direction, plus the derivative with respect to z in the z hat direction. So it's basically like a big sort of vector derivative packet, and you can, if you act it on this scalar right here, then you get a vector quantity which is the derivatives of all these scalar fields in the three different directions. And so this is what grad actually is, and it's pretty important. You're going to be using grad quite a bit in electromagnetism. This symbol, you'll see this symbol a lot, so it's very important to know what it does. And yeah, that is the gradient operator. So next we come on to the second application of this del operator, and this is the divergence. And the way in which we write divergence is with this del followed by the dot right here, and this is the same dot that I talked about earlier when I mentioned the dot product. So we're now combining this vector derivative with the dot product. So, well, if we just write it out, then we're going to get d by dx, d by dy, d by dz. That's the grad, and we're going to be dotting it, and we're going to be dotting it on, well, what can only follow here. You're only going to be able to compute this if there's a vector right here. So let's say we have a vector field called A, and this is a vector field rather than a scalar field. So temperature, I mentioned, was a scalar field, but this A right here is a vector field. So you could think of a vector field as something like a wind map or something. So the wind obviously is going to look something a bit like this. So I'm going to be blowing with different magnitudes and different directions all throughout space. So that's basically what a vector field is. It's something which has both a magnitude and a direction in all points of space. So that's just your typical vector field. And so if you apply this to A, then if we write out all our different components, then you're going to get AX, AY, and AZ. So that is what the divergence is. It's basically a combination of the dot product with this del operator right here. So if I write it out in full, then we can see that the divergence of A is dAx by dx plus day by dy plus daz by dz. Now, obviously, this looks very similar to the gradient operator I defined before, but it's actually very different. So, as you can see, this quantity right here is a scalar, not a vector. Divergence, so that whenever you take the dot product of two vectors, you always return a scalar. And this right here is just the sum of three different scalars. So this simply is the component of A, but it's not actually a vector in itself. So it's just one of the scalar components of the vector A right here, which could in theory be a function of x. So yeah, that's how you compute the divergence, but what actually is the divergence? What is it actually physically representing? Well, you can sort of imagine that at all points in space, then there's going to be kind of like a certain amount of this vector field that's entering this point, and a certain amount of vector field that's leaving this point. And we actually call this flux. This is called vector flux, and the flux is basically the amount that's going through a particular area, or in this case a particular point. And so you have vector field entering this point and vector field leaving this point. So now in theory, not all of the vector field entering will leave this region once again. So we can kind of have a look at like a volume right here. And so you can have a look and see how much vector flux is entering and how much vector flux is leaving. And this is exactly what the divergence is. Now, if you have a positive vector flux, so that basically means if you have more stuff that's leaving this area than entering it, then you have a positive vector flux, and that means you have a positive divergence. And that kind of basically means it's acting a bit like a source, because it's kind of in a sense producing stuff. You know, if more stuff is coming out than is going in, then it's kind of producing something, and we say that that has a positive divergence. Of course, the other case is a negative divergence. So say we take maybe this point in space right here, then if we have maybe a look, then we can see that there's quite a lot going in, but there's not very much vector flux coming out. So this region of space right here, this actually has a negative divergence, and so this quantity right here is going to be negative for this region of space here in particular. So it kind of acts a bit like a sink rather than a source. So more stuff is entering than it is leaving, so it's kind of sucking it out. And so that is essentially what the divergence is actually measuring. And this is very important when it comes to things like the electric field, because that will basically tell you what points in space the electric field is being generated from. This quite closely ties in with something called Gauss's law, which we're going to come on to in a few videos' time. Now, of course, you can have a region which has just as much coming in as is going out right here. So you have vector field entering this point, and you have vector field leaving this point. And regions like this are said to have zero divergence. So this quantity, the divergence of A, is zero for this point right here. And this is quite important for one of Maxwell's equations, Maxwell's second equation, in fact. And it basically says that for magnetic fields, there is no divergence. So you can never have any more coming out than you can coming in. So that is basically what a divergence of zero is. So just as much is coming in as is coming out. Of course, you could have a region of space where there's no vector flux at all. There's no vectors like coming in at all, and of course that would have zero divergence. Or you could just have like a really kind of straight vector field where it's pretty easy to tell that there's just as much coming in as is going out. So that is what the divergence is. It's all about whether things are sources or sinks. So lastly, we're going to talk about the curl of a vector field. And well, we've done the dot product, and so what happens if we combine this del operator with the cross product? Well, we get the curl operator. So this right here we refer to as the curl. And likewise with the divergence, this operates on a vector field. So there we go. It's curl A, and that will return another quantity which is also a vector. So this acts on a vector to produce a vector. So, well, how do we do it with cross products? Well, we just do, it's the whole determinant thing again, but instead of having like two components, we replace one of the components with the components of the del operator. So it's going to be a d by dx, d by dy, and d by dz along this axis. And then you're going to have the components of A, which is AX, AY, and AZ. And then you're going to have, likewise with the cross product, the X hat direction, the Y hat direction, and the Z hat direction. And so that is how you would compute the cross product, by taking the determinant of this right here. And of course, it would be in the direction. So what does the curl of a vector field actually describe? Well, the curl of a vector field describes basically its rotation, shear, or vorticity of the vector field. So let's draw out our vector field once again. Let's draw out our wind field. So this is going to be a vector field which represents the wind direction at all points in space. So this is basically a typical vector field that we get. And what taking the curl will do is basically at any point in space, it would measure how much rotation or, well, curl there is of a vector field. And best illustrated with an example. So as you can see, this region right here, well, all the wind arrows are kind of pointing in the same direction. So that basically means that at this particular region in space, then there's zero curl, there's zero shear. This side is acting just as strongly as this side right here. So we say that here the curl of this vector field is 0. But of course, somewhere like here, you can see that that this side is going to be acted on less strongly than this side. So you see that the wind right here is actually kind of turning a corner. So here, on the other hand, you'll have a certain, either a positive curl or a negative curl, depending on which way you've defined your coordinate system. So here you're going to have a curl, here you're going to have 0 curl. So it's basically a measure of the rotation, shear, or vorticity of the vector field. And another nice way of looking at it is if you have a paddle wheel, so say you've got like a little paddle wheel right here. Let's change this from being a wind field to a water field. So imagine this is like a lake or something. And here's kind of like this part of the lake is going to kind of be quite a still part, whereas over here there could well be sort of a little vortex, and there could be like a kind of a sink or something, so all the water's kind of swirling around this part here. What's going to happen to this paddle wheel? Well, the paddle wheel will rotate at this particular part of the field, whereas if the paddle wheel were over here, I hope you guys can probably see that it will just kind of carry on. It will just go in the direction of the arrows. It won't rotate. Whereas over here, it's going to like rotate like around there. And so it's going to do something a bit like that. It's not going to get bigger, but that's the best I can do. So that's that. I hope you guys can see what I mean by that. So if the paddle wheel rotates, then that basically means that that particular region of space has a curl. associated with it. And of course, curl is kind of the hardest thing to like work out, particularly if you're using not a Cartesian coordinate system. Then it can be really, really hard. But basically, that is what the curl of a vector field is measuring. And typically, we're going to define, I think from now on, we're going to define sort of this direction, which is the anti-clockwise direction, as having positive rotation. This is typically the way it's defined in lots of textbooks. And we're going to define this direction, which is clockwise, as having a negative rotation. And this is kind of in line with the right-hand rule, the right-handed coordinate system, which is typically the convention that most physicists like to use. And so basically, once again, to refer to the paddle wheel, if the paddle wheel rotates in this way, then you know that this region of space has positive curl, or if it rotates in this way, then it has a negative curl. And so now what I'm going to do is I'm actually going to expand this determinant right here, and I'm going to sort of show you a bit how mathematically you would measure curls. As you can see right here, look at all these derivatives. As you can see, none of the little components are in common with what we're differentiating it with respect to. So as you can see with the case of the divergence, then we were differentiating things only with respect to its common components. So we were doing dAx by dx and day by dy. But as you can see with these examples, we're measuring all of the what's called cross derivatives, and they're derivatives which aren't with respect to their components. So if the z component of the vector field A depends on y, then that basically means that this whole term won't be zero, and therefore the curl of the vector field won't be zero. And that basically means there's going to be some rotation associated with the vector field. A lot of the time, the curl will actually turn out to be zero, and having a zero curl actually has quite a few physical implications, which we're going to talk about in upcoming videos. So that's basically what curl is. It's basically measuring the rotation of a vector field.